In this video, we'll revise the gradient of a line segment. Now, even though this is analytical geometry, we are quickly going to revise all the properties of a gradient that we learned about in the functions section. So the first thing we learned was that the gradient of a line, AB, is equal to the difference of the y coordinates divided by the difference in the x coordinates. The second thing that we learned about gradients is that when the gradient is bigger than 0, or when it is a positive value, then the line is increasing on the Cartesian plane. So increasing means if I start on the left-hand side and I follow the line segment, then I'm moving to higher and higher values. And when the gradient was smaller than 0 or a negative value, then the line segment would be decreasing on the Cartesian plane. So if I start on the left and I follow the line, I'll move to lower and lower values. But in most examples and assessments, we'll speak about an increasing line when the gradient is positive and a decreasing line when the gradient is negative. The next property of gradients are when two line segments are parallel to each other, then their gradients are equal to each other. So in this example, the gradient of line AB would be equal to the gradient of line CD. And then we can conclude that the line AB would be parallel to the line CD. Another property of gradient is when the line AB is intersected by a line CD at 90 degrees, or when we say that the line AB is perpendicular to the line CD, then the product of the two gradients would be equal to -1. So the gradient of line AB multiplied with the gradient of line CD would be equal to -1 when the lines intersect at 90 degrees. And we can conclude that line AB is perpendicular to line CD. In this example, we want to prove that the line EF is parallel to the line CD. And we are given the points of E and F and the coordinates of C and D. So in order to prove lines parallel, we can use the gradient of EF and compare it to the gradient of CD. So let's use the gradient formula to find the gradient of EF. So it's the y of f minus the y of e over the x of f minus the x of e. And if I substitute, I have 4 minus 1 over -3 minus -5. And simplifying that, we have 3 over 2. So the gradient of line EF is 3 over 2, or we could say 1.5. Now let's find the gradient of line CD, which is also the difference of y's over the difference of x values. So y of d is 1 minus -5, which is the y of c, over the x of d, which is 2 minus -2, which is the x of c. And if I simplify, I have 6 over 4, which is also equal to 3 over 2. Therefore, we can conclude that the gradient of line EF is equal to the gradient of line CD, and therefore the line EF is parallel to the line CD. It's important when you make these comparisons that you show what you have calculated and then end with the conclusion that EF is parallel to CD. In our final example, we want to prove that line AB is perpendicular to line CD. And we will use the gradients of line AB and the gradient of line CD to prove that they are perpendicular to each other. So first, let us find the gradient of line AB, which is the difference of y's over the difference of x's. So that will be 1 minus -2 over -6 minus 1, which is equal to 3 over -7, or we can say negative 3 over 7. Next, we'll find the gradient of line CD. So it's again the difference of y's over the difference of x's. And if I substitute, I have 5 minus negative 2 over negative 1 minus negative 4. And if I simplify, that is 7 over 3. Now for perpendicular lines, we need to multiply the two gradients with each other. And if that product is equal to negative 1, then the lines would be perpendicular. So if I have the gradient of line AB and I multiply it with the gradient of line CD, I have negative 3 over 7 multiplied with 7 over 3. And that will simplify to negative 1. Therefore, the line AB would be perpendicular to the line CD. And again, it's important to answer the question by making the correct conclusion at the end and show all the necessary calculations.